The next speaker is Ermek Nurkhaidarov, and he has a very special place here at the conference and in general in life. He's the only PhD student of Jim who finished successfully and did impressive work together with Jim. And I was surprised. I had to check. I thought it was not so long ago. It turned out it was 20 years ago. So welcome, Ermek, and let's go ahead.
Thank you, everyone. I'm honored to present at the Jim's birthday conference. Thank you for organizers. Thank you, Roman, Arthur, and Vicar for organizing the conference. As Roman mentioned, I am still a student of Jim. I was a graduate student of Jim from 97 to 2004 at University of Connecticut. Probably long 7 years for Jim and short 7 years for me. My title of a talk is called The Automorphism Group of Arithmetically Saturated Model of Piano Arithmetic. The title of the talk is the same as Schmerl 95 article, The Automorphism Group of Arithmetically Saturated Model of Piano Arithmetic. I was introduced to this paper in probably 1999 by Jim, and I believe I did my what was it? A written defense for doctoral kind of preliminary defense, and I like that paper very much. And in this paper, one of my questions where Roman and Jim discusses are how much over oops. Do I still share?
Yes, you're still sharing.
Yes.
Okay, yeah. It's kind of disappeared on my screen. My screen is frozen. I'm not sure what is going on. Okay, I'm back. So very good. So in this paper, after asking how much of information about the model can be recovered from its automorphism. So I'll start with a little bit history about their topic. Probably the first paper in this direction was by K. Kosak-Koltratsky 91 paper, in which we show that if you consider two models, one will be countable arithmetically saturated, and the other one is countable just recursively saturated model of piano arithmetic, then their automorphism groups are not isomorphic. Next paper in this direction is probably Case 94 theorem, in which he showed that if we work with countable recursively saturated model of PA, then H is closed normal subgroup of automorphism group of M, if and only if H is a stabilizer of invariant K. So from this result, one can show that model of true arithmetic and even model of not true arithmetic, then if we consider these two models, then their automorphism groups cannot be isomorphic. Then the paper which I already mentioned, one of my favorite papers is Kosak-Schmerl 95 paper, in which we prove that automorphism group of a countable arithmetically saturated model of piano arithmetic codes its standard system. So using this result, we prove the following theorem. If M1 and M2 countable arithmetically saturated model of piano arithmetic, such that their automorphism groups are isomorphic, then they have the same standard system. In my paper 06, basically I wrote that as my dissertation under supervision of Jim. I showed that existence of 4 models of piano arithmetic such that they share the same standard system, but their automorphism group are not isomorphic. Jim also noticed that actually you can extend that results to their corresponding theories, completions of piano arithmetic, so that if there exist four models of piano arithmetic such that if Mi, Mj are models of Ti and Tj, then we're not going to have, when the automorphism groups are not going to be isomorphic. Schmerl in 2015 paper improved the result by showing the existence of 2 to omega of such theories. Here is the theorem from that paper. Suppose X is a countable Scott set, then there is set of 2 to the omega completions of piano arithmetic such that for every T from A, such that every T from A has representation theory equals to X. And if we pick two M and N non-isomorphic countable arithmetically saturated models, such that their theories belongs to that given set A, then their automorphism groups are not isomorphic. One more result by Jim in this direction. Schmerl in his 2018 paper used notion of thin set theorem, which is somewhat similar to the Ramsey-style theorem. And he showed that there are infinitely many completions T0, T1, Tn, and so on of piano arithmetic, such whenever I less than j less than omega, then Ti and Tj are Turing equivalent. And automorphism group of Mi and Mj are not isomorphic for all countable arithmetically saturated model of Ti and Tj correspondingly. So that's like brief introduction on the history of that topic, and then I will try to run maybe through a few definitions. I'll probably will do that really quick. So model of arithmetic, standard system is standard definition of standard system. Representation theory, you can think about that as a standard system of a prime model. Definition of recursively saturated model and arithmetically saturated model. Again, they're somewhat standard, and I guess for this audience, I'll skip those definitions. About invariant cuts. So we say I is an invariant cut if there is a sequence of definable elements in M which is upward cofinal in I, and we say I downward invariant if there is a sequence of definable elements in M which is downward cofinal in I. And we say I is invariant if it's either upward or downward invariant. Not difficult to see that if I is invariant cut, then automorphism group of M which fixes I pointwise is closed normal subgroup in the automorphism group. K in 94 showed that converse is true for countable recursively saturated models of piano arithmetic. Here is their theorem. Let M be countable recursively saturated model of piano arithmetic. Subgroup is H is closed normal if and only if it's in the form stabilizer of automorphism group of I, where I is invariant cut. And from here, this result, one can see that, for example, if you talk about model of true arithmetic, where you're going to have only trivial invariant cuts versus when we're talking about models of not true arithmetic, where we're going to have a lot of non-trivial invariant cuts. So from here, we can see the automorphism group of true arithmetic versus automorphism group of not true arithmetic that cannot be isomorphic. Okay, so for rest of the talk, if I forget, then M is always going to be recursively saturated model of piano arithmetic. I probably need to define what is smallest interstice, but so smallest interstice is consistent of all those non-definable elements which are bigger than standard cut but smaller than non-standard definable elements. Okay, so let's try to move on. There is a standard definition of a gap, but also there is a corresponding definition of interstitial gaps, which was introduced to study bounded elements. So that's the definitions somewhere here. Okay, next result is Laskar 94. He showed that if M is countable arithmetically stated model of piano arithmetic, when these models have a small index property. Basically, what the theorem is saying is that we can recognize which subgroups are open, and in the sense that if we're talking about countable arithmetically saturated models, then we have our topology given to us for free. So that's one of the reasons that when we're talking about automorphism group of arithmetically saturated models, we almost never mention, like, that if we mention the result, we will always say that it's true for automorphism groups versus the results which for just recursively saturated models, we often will say that is true for topological automorphism groups. And to an extent, that was kind of motivation for working more and paying attention more for countable arithmetically saturated models of PA. A couple of standard definitions of indiscernible elements and rare type elements, label gaps, stuff like that. Kind of want to move on and get to where the Jim's results. Okay, so how Roman and Jim 95 paper to prove that automorphism group codes for standard system, we use the following results. So the following are recognizable for class of countable arithmetically saturated models of piano arithmetic. Point-wise stabilizer of elementary cuts, set-wise stabilizer of elementary cuts, point-wise stabilizer of gaps, set-wise stabilizer of gaps, point-wise stabilizer of labeled gaps, and set-wise stabilizer of labeled gaps. So Roman and Jim proved that in their 95 paper, and then used that to show that there is a way to do the coding of standard system using subgroups. So we were looking at the subgroups which are set-wise stabilizer of labeled gap, which are in terms will be corresponding to corresponding coding on the elements, and but we're able to do a coding of standard system. Schmerl in 2015 extended that result. So he started with two models, and if there is isomorphism between these two models, then he noted that this isomorphism can be extended to isomorphism of lattice of elementary substructures. So he made that comment and that definition. Then he noticed that that automorphism will have very nice properties. So, for example, if we start with two countable arithmetically saturated model with isomorphic automorphism group, then if M sub 0 is elementary subgroup of M, then its image in N is also arithmetically saturated. So to an extent, Jim was able to do a correspondence between elementary lattice in one model versus another, and he smartly used it to prove a following theorem, which says that for any countable jump ideal X, there are infinitely many countable arithmetically saturated models M0, M1, M2 of piano arithmetic, such that if I is not equal to J, then their automorphism group are not equal to each other, but standard systems are equal to X. And the last result, which I wanted to mention in this direction, is Jim's 2018 paper, in which he so in my dissertation under Jim, I was using Ramsey theorem. Jim noted that if we substitute Ramsey for the thin set theorem, which is stated here, then if we're working with Ramsey theorem, when we can get only 4 models, because we can get RT22, RT23, and true arithmetic, and not RT22. But if we work with a thin set theorem, then we don't have that restriction because of Patti in 2016, who proved that we can always find scots at X such that it proves thin set theorem for K plus 1, but not thin set theorem for K. So using that, Jim was able to show that if M and N are countably arithmetically saturated model of piano arithmetic, such that their automorphism group isomorphic, then omega representation of first proves thin set theory set for K if and only if it happens for the second model. And using that, Jim was able to construct infinitely many completions of T0, T1, Tn, and so on of piano arithmetic, such that whenever I is not equal to J, then Ti and Tj are Turing equivalent, and automorphism group of Mi and Mj are not isomorphic for all countable arithmetically saturated models of Mi and Mj correspondingly of Ti and Tj. And I believe that's what I wanted to say about that topic. Thank you.